We can have it here in hybrid.
We can have it here.
Yeah.
We just need to.
Yeah, as long as I'm here, I might as well have it here. Writing here is okay if people see it, or what's the experience?
Yeah, just all the way down.
Right. Okay.
Did you already give an earlier lecture?
Yeah, I gave 2.
Oh, complete video. What?
Okay.
Oh, I see that one.
Yeah.
But I can somehow.
You can watch the videos.
Right. Okay.
Tell me when to start.
Do you start whenever you want to do it, teacher?
forgot how it goes. This is first time in 2 years that I give an actual lecture.
Oh, you always wait for your students to tell you at the start?
Actually, often I'm very considerate, too considerate, but year?
I lectured in April.
April last year.
Yeah.
I lectured April 2 years ago, even not April, I think, end of March. All right, so good evening, good morning, wherever you are. It's really nice to be here and give an actual class in person. So I want to do the last example, which I think it is an interesting example that people so far did not look much at. And this is an example basically due to Lipschitz and Robinson, which is really different than everything that we know, because until now, all the examples we had started their lives in examples of differentiable, k-differentiable functions in the O-minimal setting. They started their lives with a structure over the reals, and then we can go maybe to elementary extensions. We can take families in the reals and take non-standard parameter, but this is really essentially different. I'll just say a word or two about this. So let's start with the real field itself, the real closed field itself be the field of Poisson series, formal Poisson series. Let's see if I can get it spelled right this time. Right, here. Yeah, I can never get this right, never. All right, and so this is one way to look at it, is you take the formal power series over the reals and you plug in 1 over p, let's say, for p going from 1 to infinity, and you take the union of these. And another way of seeing it is all the Laurent series infinity ak t to the k over p, where n is in z, t is in n, and ak in r. Not only converging ones. And again, this is a real closed field. So this is a real closed field. And we can take k, we can call it k puis for Poisson to be the algebraic closure. That, which turns out to be the Poisson series, or it can be identified with the Poisson series over the complex field. Sorry, I will not do it. Right. Sorry. So we'll take, so this is a real closed field. I said it, and we'll take K puis to be the real closure, the algebraic closure of R puis, which can be identified with the Poisson series with coefficient in C. So this is the underlying field and its algebraic closure. And now, notice I should say, so this is ordered field. This one is ordered. And T is greater than 0, but less than all real numbers, which are here. So T is an infinitesimal. Sorry? Yeah, then all positive real numbers. Okay. And given any formal series now, I'll restrict to that. We can look, as I said last time, if you look at, in a similar setting, I noted that formal series are well defined on the elements of the valued field whose valuation is bigger than 0. And here we can look at, so H defines a function from this infinitesimal interval into R puis. So this is well defined because this is a subset of all the f in R3 whose valuation is actually bigger than 1, but in particular bigger than 0. So you can evaluate formal power series on elements here. So you get definable functions. Right? This is not definable in the field language, this neighborhood, but this one is definable in the ordered field language. Actually, the topology is the same, that the ordering and the valuation induce. So now we can look at the structure which is given by all these functions. So we can look at R3, let's call this R, with the field structure, ordered fields, and all these H's restricted to, well, we only define them here, but we can look at it like this for H formal power series. Right, so these are definitely, most of them will not converge anywhere in the reals, just formal power series.
Are you just considering one variable?
Yeah, let's for now. No, they do much more than that.
Oh, okay.
But for what I need, this is sufficient. They do actually over convergent series. This is a very small redux of what they are doing. And the theorem of Lipschitz and Robinson, following from a much more general quantifier elimination, is that this R is O minimal. And later there is a paper of Lipschitz, Robinson, and Cluckers where they put much more structure even on that. Okay, so all right. And now, how is it related to K differentiability? Because now these are, we can think of them, of all the ages, as like real analytic functions on an interval, and related to what actually the talk of Andrea Priest, we can see that they are actually can be complexified in the same structure. So it's a small fact, which is again just done by looking formally at the power series and noting, so small fact is that H can be definably extended actually by using the same power series, but you can show that the real and imaginary part are themselves formal power series in real. Maybe I need, yeah, it's possible. Now I see what Lau was saying, that I will need in several variables in order to get this to be definably extended. So yes, thanks. So I think I need this. Otherwise, it will not be definably extended. So I'm taking formal power series in several variables as well. Can be definably extended to H to the square, let's say, into now a map from here into K, the algebraic closure K3, where this is viewed now just as sitting inside K. Just by evaluating the same power series that we had in one variable, but now you evaluate it in the sense of the algebraic closure. You just like you do it with real power series. And as we said last time, H hat is a formal power series, and H hat is K differentiable on this open set inside R2 or inside K. And its derivative is just the formal derivative. Now, these are essentially new complex-like functions, and there is a paper of Udi and myself in which we answer actually a question of Lau, a very, very nice question about all minimal structures and how much they are related to the reals. And we show that this structure, or even when you restrict to finitely many functions, is not elementary equivalent to anything over the reals. And it cannot come, it's not like we took a structure over the reals, we plugged in parameters. There are differential equations that you can write that have a solution here and provably have no solutions over the reals, because to have a solution over the reals, some power series will have to converge. Okay, so I think that this is a very interesting structure, and I can only say the word that I don't know much about, but in singularity theory, one uses arc spaces. And to me, it always seemed that this should be an interesting structure to try to apply to arc spaces, because there they also look at formal power series, and I would encourage people to somehow try to apply that, because my feeling is that this should be applicable to things over the rails. Okay, to maybe singularity theory, because we have a very nice structure on the family on well, on this structure. Once it's O-minimal, of course, we have the whole theory of O-minimality that we can apply. So, all right, so this is the last example I wanted to do, and now I'll start doing really topological analysis. Okay, so now we're back to the general setting. R is O-minimal expansion of a real closed field. K, a real closed field R, not script, and K is the algebraic closure of R. And what I want to do today is to talk about winding numbers. As I said, this is the replacement to integration and power series, actually, in the setting of this general O-minimal structure. All right. So first definition is of a curve. So a actually, even if I will not say definable, I will forget to say everything I'm doing now, all the objects are definable. Okay, I'm now leaving the general setting. By the way, I put today another a set of problems to those who are interested, set of problems just about topological fields, basics of topological fields, nothing to do with model theory. If you're interested, you're welcome to take a look. If you want to ask me questions, I'll be happy to answer. So side remark. But this now is everything is definable now. So a definable closed curve in K, so it's in R2. Basically, right now in R2, we don't need to think of it as K, in R2. And I would sometimes just write the image and sometimes write the parameterization is definable, again, definable continuous sigma from 0, 1 into R2, such that sigma of 0 equal to sigma of 1. Okay, so basically it's a curve with a parameterization, to be precise, but I might not always, right? And C is the image, right? C is the image of sigma. And we will call it, maybe I'll put it here, and we'll call the curve simple. C is called simple if there is no self-intersection, of course, except the endpoints. So if sigma restricted to half closed, half open is injective. Right, so a curve like this is not simple because here and here there will be intersection. The map will not be injective. Okay, and the example that we is okay, and an example that we will go back to is S1, which I can write as all the Z in K or in R2, whose absolute value, Euclidean absolute value is 1. And for this curve, we will fix once and for all for this whole project. We will fix a parameterization, some semi-algebraic parameterization. It's some, it doesn't matter which one. One can show that none of this will depend on parameterization. Some, what is important, it will be counterclockwise. So going this way, semi-algebraic. Right? We can do it just by projecting and splitting the interval 0, 1 to 1, 0, half, half 1. Anyway, there are many ways to do it, which will realize it as a simple curve. So, and let's have just S0 to be 1. So we start the parameterization from 1 and go counterclockwise and injective. Right, so I want it to be a simple curve. So S0 restricted to 0, 1, half open, injective. It doesn't matter which one. All right. Okay, and now the idea is to start on the left side, on the domain with a closed curve, to take a map into S1 and to try to count how many times it turns around S1. So now, given any closed curve, this is one. Second, definable continuous f from C. At the beginning, we'll just go into S1. Want to define the winding number of f along C. I'm writing C at the bottom because sometimes f will be defined on a bigger domain, and I want to say on which closed curve I'm looking at. And for the beginning, we'll just say the number of times f of, let's say, t turned around counterclockwise on S1. This is what we want to capture. And actually, in the original article of Sergey and I, we do it in a fancier way, but I want to make it more down to earth. So I will try to describe a more direct way of doing that, which will give us a bit. I mean, we go through the universal cover and we get nicer results, but this will be more explicit and will give us some feeling. So how do we do that? We have, what do we have? We have, first of all, the parameterization. Sigma goes to C. We have F going from C to S1. And now we want to go back. Okay, it's not injective S0, but I will write S0 inverse, meaning I just forget about 1. Okay, so the only non-injectivity of S0 is at 1. And I just forget about S1. So I'm just taking it on the half open, half closed, half open, half closed. And we let F hat be the composition. So what is it? It's sigma first, F afterwards, S0 inverse afterwards. And this is from half open to half open. And let me, for simplicity, we can always adjust the parameterization of S0 just by turning it around. So I move S0 if needed because I want F of sigma 0 to go to 0 at the end. So let's assume this is, I can just do by changing the parameterization over there. So without loss of generality, what do I want to say? S0 of 0 equals to what I get from here, equal to F applied to sigma of 0. Okay, so I need to adjust S0, possibly. And now let me draw a picture of what we get. So first notice that the only problems in terms of continuity will happen in the places where f reaches the point 1 on the circle, because away from that, we didn't do anything. The only problem is that S0 is not, I mean, that we removed 1 from the image of S0. So we get something like that. So let me write it first. Okay, another assumption I want to make for simplicity. Assume that f is nowhere locally constant. Is not locally constant anywhere. If it were, you just cut away, you cut out this part where it's locally constant, you glue on the side and maybe you reparameterize, but it will not affect the picture that I'm going to draw, and this will be slightly simpler to describe. Okay, so it's not a big deal to assume that. And now let's look at f hat. So f hat is the composition. All the places where it hits 0. And I'm saying that this is the only possible discontinuity of f hat. Just the places where this is 0. So these are only possible discontinuities. Of f hat. And by O minimality, this is finite because we assumed it's not locally constant. So that's S0, and I will draw the picture in a second. B, so the way we chose it, sigma of 0 will go to 0. I mean, 0 will go to 0 because of this assumption. So we will get 0, A0, A1, AN, and this is again, no, this is not, just a second. What do I want? Yeah, this is fine. Yeah, because at the end it also will go to Sorry, this is 1. This is 1. But 1 is not in the domain, right? So okay, so let's leave it like that for a second. Doesn't matter. Less than 1. And here's the picture that we got. We get something like that. So 0, 1, 1. It's not symmetric, but it's okay. We might get something like that. This will be A1, A0. Here, maybe we went on the circle and went back and got out of here. This is A2, A3. Maybe we remember that these are places where f hits 1 at the image on the circle. And maybe just when we hit 1, we went back. So we will do this. And then maybe we go around the circle and we go to here. So this is A4. Okay, this represents crossing the circle counterclockwise, right? If this is the circle, I'm looking at the image of f. This represents, this A1 represents going this way. Here, it represents going this way, around 1. This special thing represents the situation when we went to 1 and we came back, right? So this is a very non-generic behavior. Just exactly at 1, we came back, and here we crossed again and came out of here. Okay, so you play with that, and you see how a map from a curve into S1 will look like that. And now we can define the winding number. But to define the winding number, I want to add I need to do one more thing, but I want to call, I want to write this, add this. Add 1 as a point, even though we never reach 1, it's not in the domain, but add 1 as a point. And now, for each AI, let's write f of AI plus the limit of f of t as t approaches AI from above. And let's write fi minus the limit of f of t as t approaches AI from below. And notice that this is always either 0 or 1. Right? Because it corresponds to approaching 1 on the circle, and 1 is either 0 or 1, depending from which direction you're arriving. But as a function, since 1 is not in our range, the values of the function will always be here. Here, it's not defined at all. But so this is what like unwinding the curve will look like. And now we can define the winding number. And the winding number will just be the sum of these differences. And this will tell you how many times you went around S1. So by definition now, the winding number around as f restricted to C going into S1 is the sum. I goes from, is it 1 or 0? Depending how I parameterize it. I goes from 1 to n of f of AI plus minus f of AI minus 1 minus. I'm taking, I'll do it in the, we'll go to the example in a second. Each one of these is either 0, 1, or minus 1. So the sum is always in Z. Let's see what we get here. Okay, I'm going to the example. Here it's 0 and 1. So this contributes 1. The difference, right? The limit from the left. Sorry. It's the other way around. Sorry. You have colors? This is the difference, the limit on the left of the next one minus the limit on the right of the previous one. Sorry. All right, so the limit here is 1. The limit here is 0. So this interval contributes 1 to the winding number. The limit here is 0. The limit here is 0. We get here 0. We didn't turn around. Here, the limit is 0. The limit here is 1. So we get here minus 1, 0. The last one is minus 1 again. Right? So altogether, in the example, the winding number of f along C is 1 plus 0 plus minus 1 plus 0 plus minus 1 equals to minus minus 1. Which means that altogether we did one turnaround clockwise, as t moved from 0 to 1. We did one turn clockwise, clockwise, on S1. That's it. So this is the definition of winding number. And now let's make some basic observations first before I do examples. Note, I already said that the winding number is always an integer because we just sum 0, 1, minus 1. Now there is something, it's an exercise. This whole process that I described here is uniformly definable. So if you have a definable family of functions, you can do it for each one. There is a bound on the number of zeros. So there is a bound on the number of AIs, and you can do this uniformly in families. So if FT, T anywhere, the definable family is a definable family of continuous functions. They don't even have to be from the same C. They can be from a family of CT, from a definable family of closed curves into S1. Then this is definable. What do we mean by that? Then for every n in Z, the set of all T such that the winding number CT of FT equals to n is definable. In particular, it is bounded in T. Why? Because the number of zeros by O minimality is bounded. Okay, so I should say maybe I will put here and bounded, and this is very much by O minimality. Uniformly bounded. This is crucial point in the whole development of complex analysis, the fact that within families, the winding number is always bounded, finite and bounded. Let's look at some basic examples that we know. So I'm taking examples from complex analysis, but there is no need. All of this is just for continuous functions. So examples, if the function f of z is z squared, and let's say from S1 to S1, so the curve C, the domain, is S1 itself, then when we do this unraveling, we will get this picture. We hit twice. We hit twice 1. So we get like this, and then this contributes 1, this contributes 1. So the winding number is equal to 2. But the same thing is true even if you look at fz equal to minus z. This does not change. All you have to do is shift. But since we are making this shift, where is it? When I assume S0, 0 equal to f of sigma 0, we'll get the same picture after the shift with f of z. Of course, if we know it from complex analysis, but so after the shift, we will get that. If we do it before the shift, the definition has to be slightly different, then we will get something like that. Like that. This is within shift, but I prefer that we start everything from 0 and go back to 0. So this is, we will not get that. Okay, so the winding number of minus z squared is also 2, as it should be. And the way to get negative is to go clockwise. And for example, we know 1 over z cube or something. So if f of z equals to 1 over z cube, again from S1 to S1, then when we unravel, we will get something like that. This is what we will get for f hat. Over there also, these are the pictures for f hat, this composition. And then we get minus 1, minus 1, minus 1. So the cube around S1 is minus 3. All right. So now we have a notion of a winding number or definable continuous function so far from a closed curve into S1. Right? The curve does not need to be simple curve, the domain. Now I want to write basic properties. Some of them I will point out why they're true, and some I will not, unfortunately, because the time restriction, but at least in two of them, I hope I can convince you. So we already saw that it's uniformly definable in parameters. Well, I think if you have some experience in nominality, you can see that all of this process can be done definably uniformly, and there is no problem to do all of that. Let's look at this one, very important. If f from C to S1 is not surjective, then the winding number is 0. Why is that? Let's look at the picture. What I'm saying that if it's not surjective, it means you don't cover in the range the whole interval 0, 1. So you will never have jumps like we have here from 0 to 1 or from 1 to 0, because otherwise it will be surjective, right? So none of these intervals we can get the value 1 or -1, right? So it's not just about the sum. Locally, in each interval, you cannot get 1 or -1 because otherwise you will be covering the whole range. So it means you are surjective. So how will it look like? Well, it looks like something. Maybe you go and you go back, and then maybe you come out of here, maybe something like that. And then maybe you come out of here, something like that. Right? Because you cannot hit all of them. So you can never go from 0 to 1 or from 1 to 0, because then it means you are surjective. So the picture has to look like that. And then each interval like this, you just get 0. Right? The limit here is 0, the limit here is 0, so it's 0. And each here the limit 1, this limit 1. So we'll get 0 in each interval. So the whole thing is 0. Right? So none of the intervals contribute 1. So none of the intervals, because this exactly means that because of continuity that it will be surjective. AI, let's do it like this, AI minus 1, AI contributes 1 to the sum. Okay, next one is a bit more hand waving. This, I think this is very easy to translate into a formal argument. Two. This is about invariance under homotopy. So let me say exactly what I mean. Everything defined. If Fg from C to S1 are definably homotopic, and I will say what it means. Homotopic, and let me write what it means, which means that there is a definable continuous H from 0, 1 cross C into S1 with the property that H0 of anything is exactly F of that, and I can write T here, T, or maybe not T, T is usually for time. Let's write it X, and H1 of X is G of X. Then the winding number is the same. The winding number of F equals than winding number of G. And now I will hand wave over that. What is the idea? Well, first of all, let me say that because 0, 1 is continuous interval, is a definably connected interval, we really just have to show local constant. The fact that H, so we only need to show, need to see that the winding number, how shall I write that? Of H T X C is locally constant. Oh, I don't need the X even. So for every T, we have a function from C to S1 is locally constant in T. Because 0, 1 is definably connected. And the reason this is true, I'll go to the picture, is when you do small perturbations of the function, you will not change an interval like that. What will happen that the intersection point might move and you'll be here. So you will intersect, you will go across a 1 in a slightly different place. But you will not change the fact that this will contribute 1. You might change A1. The same thing here, you will not change between A1 and A2. It will still be 0, but maybe slightly moved around. The only places where something substantial can happen is at places where it turns around at 0. If it turns around if it goes to 1 and comes back, then maybe after the perturbation, we'll get something like that. But this anyway contributes to it. So, or no, if you go to something like that. But notice that in this case, the contribution from here to here will be exactly like the sum of contributions from here to here, or the sum of contributions from here to here. So the only places where things can go wrong is where the function changes its mind exactly at 1. Right, on the circle. It goes to 1 and comes back. When you move it a little bit, you might get less points. But then we just have to verify that the change between the previous point to the next point is exactly the same as the sum of these two changes. For example, here, this is -1, this is 0. When, sorry, this is -1, this is 0. Now I'm worried. What happens if I disconnect? No, this is not good, right? I have this. And now I have, yeah, you cannot go to here. Yeah, you will have to go to here. Right? If the function goes in this direction, you will do that. You will get -1, but just in a different way. It will be -1 plus 0 here, and here it will just be -1. And if you went, and if you did something like that, and you disconnect after homotopy, then you will get 0, but just you'll get 0 in a different way. Here you'll get -1 and 1, and when you disconnect and you move it up, you will get 0 in this way. So I'm saying that the only problematic points are points like this, and you have to convince yourself that maybe you move a little bit, the winding number does not change when you make this continuous perturbation. Okay, so this has to be checked. But again, it's believable. You just have to go through only through points like that and see what happens and look at the all. I think there are 3 possibilities of what can happen. Okay. The last one is more problematic because I don't think I can justify it at all using this definition. I think there should be a way to justify it, but I think it will be very unnatural. And this is how winding number behaves with respect to multiplication in S1. So S1 is a subgroup of K. We can multiply. So the winding number of F. So we have 2 functions again, F and G from C into S1. And now we can multiply inside S1 or inside K. Multiplication in K or S1. right? We're multiplying the complex field, right? And here, it turns out that this is the sum of the two winding numbers. And this will be hard for me to justify using this definition. I tried to think of something simple, I could not. It's interesting, there should be a way to justify it from that, but I couldn't find. So the only reason I could see immediate is just what we do in the paper, use the different definition that goes to universal cover. And then this comes out very naturally. Maybe the other properties become complicated, but this is very naturally use alternative definition of WCF. So via universal cover of the circle. Okay, so I think this is one of the largest hand waving because, yeah. But I'll be curious if anyone finds a nice proof of this fact from this kind of definition, it would be very nice. But like,
if you have a restricted sign and cosine in your language,
yes.
Wouldn't that be possible to copy mostly classical proofs?
But don't the classical proofs of winding the definition go to integration?
I thought.
Oh, I mean just you mean in continuous.
Well, I have to look something up. I thought that I had seen some arguments that basically use restricted sign and cosine. But anyway, you don't assume that you have that in your language anyway.
Yeah, I cannot imagine that. Actually, I'm taking back. It doesn't have to. I mean, this is totally topology. This is not about analytic theory. So there should be a reasoning which has nothing to do with integration. I would think.
Yeah, I understand. But okay, I have to.
But I cannot imagine that sine and cosine will simplify. I don't know.
Okay,
all right. Yeah, I'd like to see that. Okay.
Kobi,
Yes.
another question, please.
Yes.
Why do you take S0 to be semi-algebraic?
Just to have it in all my structures, because I'm going to work in expansions of. I should have said maybe something else. None of this depends on the parameterization either of sigma or of S0, because the shape of this function, just the winding number comes out of this shape. So if you change parameterization, maybe they will be squeezed to the left, to the right. So none of this, I should have written this. It does not depend on parameterization. I just wanted to have something that exists in all expansions of real closed field, just that. But it doesn't have to be. You can take any parameterization. If you have sine and cosine, take the natural parameterization. But I have doubt that this will help. Maybe I'm wrong in proving this property. But maybe I'm wrong. All right, and maybe the last property I want to put here is that if you go on the original curve, if you go the opposite direction, so you reparameterize it not from 0 to 1, but from 1 to 0, the usual reparameterization, then you get. So what do I mean by that? If you look at the winding number of C along C, and then you look at the winding number of C in the opposite direction, you change the direction of the parameterization, you get minus. The reason is that every increasing function will become decreasing. So between 0 and 1, it will be going downward. So every one will become -1 and vice versa. Right, so just changing the parameterization, reversing parameterization of C. That's what I mean by that. All right, so we have a notion of a winding number for a function from a closed curve into S1. Now we want to get something more general. So the next notion of winding number is not only from maps into S1, but maps into K, into R2. So assume F now is a map from the curve. This is again a closed curve into R2. Okay. Okay, and now it's definable continuous. All these maps will be, I will be measuring winding number will be continuous. And now let's pick W0 in K, but not on the image of the curve. Okay, so the picture is the curve may be doing something like that. This is f of c. And we pick W0 somewhere here. Now we can convert this picture. What I want to do is to define the winding number along C of F around W0. And I want to count how many times we turn around counterclockwise W0, the point W0 as we move. Remember, C as a parameterization as we move from 0 to 1 on parameterization. And the simple way of doing it is really project everything onto the sphere centered at W0. So I can put the sphere anywhere, but let's, just for simplicity of the picture, let's put the sphere inside. It doesn't have to be inside. And I'm just projecting. And just projecting all the points onto this sphere. Okay, but I will normalize because I want it to be into S1, but you just project everywhere into the sphere. And the formal way of doing it, we define first, let's call it, I don't know, F bar. And F bar will be from C to S1, just F bar of Z will be F of Z minus W0, and now normalize to put it inside the unit circle, F of Z minus, and this is now in S1. Right, so you could just put a circle of radius 1 outside and project it outside, or you project it here and then you normalize. But you go at every point, you connect to W0, and you project onto the circle centered at W0, and now shift everything to make it S1. And now, by definition, the winding number of F around W0 is, now we have a map into S1. So now it's the winding number of C of this function. Right, this is well defined. We just defined it. Let's call it the winding number of F. Call it the winding number of F restricted to C around W0. W0 is in the image, right? Not in the domain, in the image. Yeah. All right, that's it. This is the topology that we need. And now, first, let's notice that there is also already a strong connection to differentiability in the complex, in the K sense. So winding number and K differentiability. Statement. Assume we have F. All my U will be open in K, open subset of K, definable. No, we don't need continuous even. Yeah, continuous. Sorry, continuous. And inside U, let's pick a point where f is differentiable. And k differentiable, so differentiable in like the complex sense, differentiable at some z0 in U. Right? Just means that f of z minus f of z0 divided by z over z0 in k has a limit. If the derivative at z0 is different than 0, then for all sufficiently small circles C centered at z0, centered at z0, the winding number of f along C around the image of z0 is +1. All right, so we have U, we have z0, we have something in the image, we don't care. And the claim is that if the derivative is not, if f is differentiable at z0, then if you take small enough circle here, whatever it does in the image, the winding number eventually will be 1. The total times you turn around by f0 is 1. This is the first time that differentiability will play a role, because what I did so far had nothing to do with that, right? It was just topology. Proof. Let h of z be f hat, f bar, what we call, which is f of z minus f of z0 divided by z minus z0. This is a map into the unit circle. And now we'll define auxiliary function k of z. Let's give a name to the derivative. The derivative is some k number. Assume that d will be equal f prime of z0, which is, we assumed, is different than 0. It's not? Yeah. Sorry, it's not f bar. Sorry. You're absolutely right. No, it should be fz. Thank you. It should be here. I wanted it to be f bar, so now it is. Thanks very much. F of z. Sorry, minus f of z0. Sorry. Thank you very much. That's what I wrote, but yeah. Thanks for noticing. Right, so now it is f bar, right? I hope I can, thanks. All right, and now let's define k of z to be a very simple function, d times z minus z0 divided by the norm of this, by the absolute value of d minus. So these are two functions into S1. Right? Both of them from C into S1, or from U into S1, and this is actually from K, I guess, minus Z0 into S1, and this is not exactly U, all the places, yeah, so all the places where f of z is different than f of z0. Okay, so let me say first thing is because the derivative is not zero, there should be a neighborhood of z0 where f of z is different than f of z0 because it's differentiable. If it was equal, we will get the limit equal to 0. So since f prime of z0 is not 0, there is some u1 inside u, z0 inside u1, such that f of z is different than f of z0. That's why I can divide for all z in u1 except z0, right? Because this is just basic definition that right, we know it's differentiable. We don't have to prove it's differentiable. So if you had arbitrary closed places where the numerator is 0 in the definition of a derivative, you will get that the derivative is 0. So there should be a punctual neighborhood where the derivative is not 0. Where the function, sorry, is different, and then that's why we can divide. Otherwise, we couldn't divide. Okay. Now, as for z, very close to z0, because the derivative is d, notice that this quotient is just very close to 1. H of z divided by k of z is very close to 1. Because you just get the definition of derivative as you do that. But this implies that the function h of z divided by k of z, which is also a function from c into S1, has its image very close to 1 for c sufficiently small. For c sufficiently small is non-injective, is non-surjective because the image will be very close to 1, as it says. Has image close to 1, so in particular it is non-surjective. So h over z over k is non-surjective. But then the winding number of a non-surjective function is 0. So the winding number of the quotient will be 0. Follows what we said before, right, earlier. The winding number along this small c of h over k is 0. But now we use this homomorphism, the fact that the winding number of a product is a sum and the winding number of a difference is of a quotient is a difference. And this is the winding number of c of h minus the winding number c of k is 0. So the winding number of h, which is f bar, I remind you, equals the winding number of this very simple function d z minus z0 of d z minus z0 divided by the absolute value and this is very easily seen to be equal to the winding number of just dz. You translate everything to 0, d times z, not to confuse, over the absolute value of d times z. And this is a small computation. It's basically the identity is 1. So you can verify, and this is exactly by definition the winding number of f, sorry, around. Okay, so we replace the original f, well, with f bar. This is always true by definition. And then because these two behave very close to each other, very similar to each other, near z0, then actually we can replace the computation of the winding number of f with the winding number of a very simple function. And this is very easily to see. This is basically like z, just translated by d, but this is basically by d over d bar, but d over absolute value of d. And it's easy to see that the winding number of the identity is just 1. Okay, so a lot of what we are doing, this is behind it. The fact that at least at places where the derivative is non-zero, you take a sufficiently small circle, the winding number is just 1 around f of z0. Okay. And now we come to the heart, I think, of this is probably what I will write now, the heaviest result here that most of things follow for me. So I will try to be, let's see, more detailed than I might be later on. So first of all, let's fix notation. Let's write D now for the unit closed disk, closed unit disk in R2 or in K. And let's write, for now, C will be just the unit circle. It will not be a general for the theorem that I'm about to write. Okay, I can write it D1 and C1, but somehow in everything that I will do now, this will be fixed. It will be the same D, the same C. And the main lemma, I think, in the whole, at least the theory in one variable, is the following. Assume that F from D, from the closed disk to K, is definable, continuous on D, on the closed disk, and differentiable in the interior of D. And F is K differentiable on the interior. And I will say at the end that this is important, that actually we could have even had a weaker assumption that it's differentiable on a codimension 1 set. So we can even remove from the open disk a set of dimension 1, and none of the arguments will be affected. But for simplicity, let's do the proof in this setting. And now let W0 in the range be in K, but not in the image of the unit circle. Okay, so the picture is the image of the unit circle is here. We don't know where the unit disk is going. We'll talk about it soon. But all I need is that W0 will be either here or here. I just want it to be outside the circle, the image of the circle. One, and this has nothing to do with differentiability actually, if W0 is not in the image of D at all, I think it will mean that, okay, that probably, I'm not sure if this picture can happen even, but if W0 is not in the image of D, then first of all, the winding number of C, of F, sorry, along the unit circle around W0 is 0. So I guess this picture probably cannot happen, the one that I drew here. 2, and now 2 and 3 are the crucial points. If W0 belongs to f of d, but remember it's not in the image of the circle. It's still not in the image of the circle. Then the winding number of f around W0 is always positive. And the last one, you look at f at k minus f of c. Notice that f of c is definably compact because c is definably compact. I'm not sure if Garrett spoke about definable compactness, but anyway, it's closed and bounded. The image of a closed and bounded, here everything is subset of c of k. So this is closed and bounded or definably compact. I'm not sure if it's needed. But anyway, it's closed because the domain was closed and bounded. The image of under continuous map is closed and bounded as well. So the complement is open, and by omnimality, it has several definably connected components. Like here, we have one component, 2, 3, 4, and I guess one outside. 1, 2, 3, 4, and 5. Here we have 5 components outside. And the point is that every component of k minus f of c, so this actually has nothing to do with W0, but it will follow from what we do in 2, is either fully contained in f of d or disjoint from f of d, or disjoint from f of d. And this is a bit hard to grasp. So let me give you an example where this fails with real functions. Nice continuous functions. Okay, so in order to understand what it says, I think it would be easier if we look at an example and see what happens. That there is something, this is very special. Well, as I said, 1 will be true, I think, just under continuity, but for 2 and 3 will not be true in general. Okay, so example where 2 plus 3 fail without differentiability. And the example is f of xy equals to x y squared. What happens here? Let's look at the unit circle. What is f of c, f of the unit circle? Well, this is defined everywhere, of course, but as we go from along the upper half arc of the circle, we will do something here. I'm not sure, it will not be a circle anymore, but it will be maybe something like that. I don't know how to draw it even. I'm not sure even I'm drawing it correctly. But as we go here, we will go here. I will not put the x-axis for now. And as I go here, I will actually go back. Right? Because of the symmetry in y. So f of c is just, I want to erase all of this. This is f of c, just this upper half. This upper arc. Right? Because f of x minus y is the same as f of x y. It's symmetric in y, so whatever we did here, we're just going back. All right, so notice that k minus f of c is just one component, right? So k minus f of c has one component. Just everything, the complement of this arc. Now, if you see, so what happens to f of d here? Again, because of symmetry, whatever happens in the upper part will be happening in the lower part. And what you can see is that this part, what color Oh, I don't have any more color. All right. This part will go to here. And the rest will go here. But notice this is not f of c. Not in the frontier of the image, the boundary of the image did not come necessarily from C. So look what happened. First of all, because this is a map, you can see easily that if you take any W0 here, the winding number will be 0 because it never closes even around W0. So the winding number here will be 0 around the winding number of F around W0 is 0. But even more importantly, the component K minus F of C, part of it is inside F of D and part of it is not inside F of D. So 3 fails, right? The only component we have here is split into part of it which is F of D and part of it which is not F of D, and 3 fails as well. Now, I just wrote this x squared to make my life simpler, but you can easily fix this because it might look to you like there's something special going on because we went back along, but you can easily fix this function. So you will get here something that goes back not in the same way, goes back a different way, and all these problems will still arise. You'll just get 2 arcs very close to each other as the image of C. Okay, so even for a very simple function, you can see that K differentiability behaves differently, if this is true, than R differentiability. This is definitely R differentiable. All right, so now I want to spend the rest of the time actually proving this. As we'll see in as many details as, it will not be fully detailed, but okay, so let's prove 1. And for 1, there is no need for differentiability, as I said. If W0 is not in F of D, let's see that the winding number is 0 around W0. The reason for that is that we can shrink now continuously. Shrink. So let's say we have W0 here, and here, I don't know what mess we have here. This is all F of D. Shrink C continuously. As C approaches 0, right, which as the radius of C approaches 0, F of C will be smaller and smaller. Will get closer just by continuity to F of 0. What do we get at the end? Not at the end, as we get close to the end. So now we have W0, and F of 0 is somewhere here. So the whole image will be here, very close to F of 0. But now, if you do F bar, right, if you now normalize it and you move it to a map on S1, so now F bar from C into S1, the image of it, well, W0, what do I want to say? Yeah, the image of that, what we are looking at, right? F of Z minus W0 divided by the norm of this. what we will get in this picture, we will get the image is somewhere here. This is the image. Right? Remember what we do? We take a circle here around W0 and we project onto the circle. We can assume the circle is radius 1, or it doesn't matter where it is. We will get a small part. The image will lie on a small part of S1, so it will be non-surjective. Right? So the image is not full of S1, so this F is not surjective. F bar is not surjective. So F bar is non-surjective, so its winding number around W0 is 0. And because we moved continuously and we said that this can be translated to continuous homotopy if we want. So image of F bar restricted to this C small c is different than S1. We just will cover a small arc, maybe inside S1. So the winding number of F around W0, this new C, small c now, is 0. But because we moved homotopically, we moved continuously. So by the homotopy equivalent, by the homotopy statement, by the homotopy statement, WF around W0, the original, right? This is now unit circle, is 0. So if W0 is not in the image, the winding number around it is 0. Okay, and there was no differentiability here at all. Okay, so the core is 2 and 3, as I said, because this is really where K differentiability should come in. And I will try, let's see how detailed I can do it. Tamar, can you remind me how long do I have?
Till 10 to 11.
10 to 11, okay. So now proof of 2. We say that if W0 in f of d, then it's positive, right? Notice that we can never get negative. Always get 0 or positive. Okay. So now I will do it via several steps. So now we have W0, first of all, is in K minus the circle. Otherwise, we couldn't even compute the winding number around it along C. And now W0 is in, sorry, I want to do the following. Yeah, W0 is in FD. And let's fix a definably connected component of K minus FC, the one that contains W0. Let W of C be the definably connected component. There are finitely many, doesn't matter actually, component containing W0. And because f of c is closed, the connected components are open. So this is open in K or in R2. And W0 is in it, right? So we have the picture is maybe something like that. I don't know even where f of d is, but W0 is here, and this is W. First thing is, notice that f of d intersection W is infinite. It already has W0 in it, because this is in f of d, but it has to be infinite. Why? Because f of d is definably connected. F of d is definably connected because d is definably connected. So W0 cannot be an isolated point of f of d. So W0 is not isolated in f of d. So it must be the case that inside W, you have a whole infinite set inside f of d and W, right? So the only way that this can happen is this f of d intersection W is infinite. We cannot jump from f of c, right? F of c is part of f of d, but we cannot jump from here to here without having actually a definable path, but I don't even need a definable path. All right. Next, two. Let's consider the pre-image under f of W. F is a continuous map. W is open. We don't know, of course, that f is surjective on W at this point, but still, it's the pre-image of an open set. So this is open and non-empty because it contains Z0 and non. Actually, there is no Z0, but it contains the pre-image of W0. Well, it contains the pre-image of that, which is an infinite set. I'm claiming now, okay, the set of all Z in U such that f prime of Z is non-zero has dimension 2. Cool. So this is an open set. If not, then the set of all Z in U such that f prime of Z is equal to 0 is dense in U. But this is a closed set. Actually, do we know that it's a closed set? No, we don't need that it's a closed set. We don't need that it's a closed set. Let's call it U. Let's call it X. Even not dense, it's codimension 1. Has codimension s or equal to 1 in U, right? Because the complement is exactly the places where the derivative is non-zero. But if the complex derivative, the k derivative is 0, in particular the differential, the R differential is 0. So now if we look at f restricted to x, from x to k, you might have to split it into connected components or even to piecewise C1 components as differential 0 everywhere. everywhere. So possibly after partition, the image has to be finite. It has to be constant on each component. But then after partition, F is constant on each component. But then F will take only finitely many values on X. And because F is continuous on U, even now we don't need the derivative. So F of U will be finite. Right? By continuity, if you have a dense set of U in which you have finitely many values, then F takes only finitely many values on U. But this contradicts one, because we said that inside W, F of the intersection W is infinite. So this contradicting one. All right. Next. Okay, so now pick Z0 generic. It will be easier. I can work with dimension all the time, but I think it will be easier, and I want to get a little bit people used to work with generic inside X. So, okay, so there are several steps here. In order to realize generics, we have to work in a sufficiently saturated structure. So my claim is that all of this is first order statements. So if there are two in one structure, they are true in any elementary equivalent structure. You can take this picture, go to elementary extension, which is sufficiently saturated, and realize generics, right? So if needed, it's not necessary. You can do everything in terms of dimension all the time, to say the dimension, the codimension, but I like working like that. Move to elementary extension. Side remark, this is first order, so we can do that. Remind you what you mean generic. So let's assume over the empty set. So I'm assuming that all the data is definable over the empty set. Assume F is definable over the empty set. If not, just add it to the parameter. So what does it mean to be generic? I remind you, it just means that you avoid all subsets of smaller dimension. So in particular, F is C1 because it's C1 at Z0 as an R function, right? This is part of, I think, what Garrett did in all minimal structures. Functions are piecewise Cn outside set of smaller dimensions. Z0 is generic, so everything nice happens there. And because its derivative is not zero, Jf restricts the Jacobian of F at Z0. How do we write this? I guess like this is invertible. Because F prime of Z0 is non-zero. You'll see in a second why I need that. So by the inverse function, by the inverse function theorem, it means that the image of F in a neighborhood of Z0 is an open set, right? So F of some U1 inside the connected component W contains an open set at least. I'll say a second what is FA1 contains an open set. And this is by the inverse function theorem. For all minimal structures, U1, well, I guess I could just have written U, because if it contains an open set, then f of U contains an open set as well. I didn't say it was open, I just say it contains an open set, right? Because if the differential is invertible at a point, then the image contains an open set. I want to keep this on the top. So now look what's happened so far. We showed that FD intersection W is infinite, but now we showed that FD intersection W contains an open set. So it's a bit better, of course. So FD intersection W now contains an open set. This is what we have so far. We really did not use even that strong, we did not use K differentiability. It was enough to, I think none of this uses K differentiability. We could have looked at the places where the differential is either invertible or not. And I think the same argument so far would have worked. All right, now pick W1 in FD intersection W generic as well. So now we're in the image. And I think I will reach some point, we'll collect some information and we'll stop in what I want to do. And the claim is, and after the proof of this claim, I will stop. We have two properties. F inverse of W1 must be finite. Right, so generic, I remind you, it means that the dimension now of W1 over the empty set is 2, because we have an open set. So to say that W1 is generic, it means that it's independent in the plane. 2, for all Z in this pre-image, which is finite, F prime of Z is different than 0. So I'm saying that if you pick a generic point there, first of all, the pre-image has to be finite. And notice that we don't know all these identity theorems that if the pre-image is infinite, then the complex differentiable function has to be constant. None of this is known, right? We only know what had on the board, more or less. Nothing else. So we are aiming still to get all these basic results from complex analysis, we are still not there. Let's just see why 1 and 2 are true. 1, if F inverse of W1 is infinite, let W1, big W1, be the set of all W inside F of D to section W, such that F inverse of W is infinite. This is a definable set. Being infinite, right, is definable in omninormal structure. You just have to say that the projection on some coordinate contains an interior, or dimension is definable. And this set now will contain our generic point W1. It is 0 definable, so it has dimension 2 because it contains a generic point. Dim W1 is 2. But then every fiber is infinite. So now we have F, some F inverse of W1 onto W1 with infinite fibers, but this is impossible because this has dimension 2 and this has dimension 2. And if every fiber is infinite, the image should have had dimension 1. With infinite fibers, and this is impossible because we should have had the dimension of F inverse of W1 greater than the dimension of W1, but this is already the maximum is 2, and this has to be at most 2. So this is a contradiction. Right? So I'm using here the fiber I. Can I go 3 more minutes? And what is the rule? How strict are you on this? Let me do 3 more minutes, okay? And usually I tell my students I will give it up to you. I will give it back to you in the next class. And I do actually, but I'm not sure I will do it now. But let me just finish this because I want to start next time from these 2 claims. And so let's look at 2. We want to show that every pre-image has a non-zero derivative of this generic point. So assume that there is Z in F inverse of W1 F prime of Z equal to 0. Again, let W2, if we want, be all the W in F D intersection W such that this property holds, its first order property. It contains W1, so has dimension 2. Dim W2 equals to 2. But now, by definable choice, we can choose for every point here one element like this, right? So by definable choice, there is x1 contained in K such that for every small w in W2, there is x in x1 with the derivative is 0. And in fact, for all x in x1, the derivative is 0. And in addition, and so we just choose for every w, here we choose a pre-image with the derivative 0. And for every x in x1, f prime x is 0. I'm talking about the k derivative. And again, we have f from x. So here something mysterious because there is an overkill here, it seems. So we again have a function of this is dimension 2 because we have a definable function which picks pre-images. So this has dimension 2 because we have a definable function going here, which is actually a section for f, and this has dimension 2. But here, the differential, the R differential is 0 everywhere, so the image should be finite. So it's a little bit, yeah, so maybe there was a way to avoid that. But again, JF restricted to X is actually 0 for all X in X1, and the image is 2, and this is impossible. You cannot have, yeah, of course, yeah. The image again should have been finite and not. So, sorry, I'll stop here and I'll pick it up from here, from these 2 facts, and then we will do winding numbers. Okay, I didn't do any winding number at all. So far, I just massaged the situation, and all of this can be done just because of ominimality. You see, I'm using ominimality all over the place here. All right, so I stop here. Sorry, I went over time. 3 minutes. Yes, yes. You're both going to getting an answer.